I'm Seonghyn from NLCS Jeju. But before I begin my presentation, I want to ask a simple question to all of you. So, why do you like mathematics? Okay, I think that everyone has different answers to this question, but one of the biggest reasons why I like math is because math grants us the opportunity, the power to calculate things that would have been impossible to calculate if we did not have that. So, for instance, I can just sit on my table and using some differential equations and physics, and with the aid of my computer, I can perhaps calculate the orbit of a planet around the sun or whatnot. I can calculate those kinds of things that would have never been able without the aid of mathematics and logic. And mathematical modeling, which I'm going to present today, is an important branch of math that really embodies that kind of power and that potential of mathematics to really be applied in our daily lives. So this is what I'm going to present today. First of all, I'm going to give you an intuitive understanding, a basic grasp of what mathematical modeling is, and then I'm going to tell you about how we actually construct these upon 7 steps of modeling, and then finally I'm going to give you a short application of something called system dynamics models, which I'm going to tell you about the meaning, and then go through a short run-through of an actual construction of a model. So first, what is mathematical modeling? Because it's a really big word. It's very confusing. So let's have an intuitive understanding of what this actually is. And here, this is like 20 data points of GPA versus time spent studying per day of high schoolers. On the x-axis, you have time spent studying per day, and on the y-axis, you have the GPA of these students. And just using Microsoft's like Excel or spreadsheet, you can get this equation here. And you can just see that this equation quite well represents the 20 data points in there. And here, this is also a math model. And here, X is time spent studying per day, and Y is the GPA of these students. So already by simple calculations, by this really simple equation, you have a model that represents time spent studying per day versus GPA. But while these simple things are models, these things are also models as well. This is actually something that my school math teacher wrote. This is a discrete models for in vitro tissue growth. So that is tissue growth that happens within a test tube. And here, this looks much more complicated and intimidating than the one I showed you before. But this one is also a model. So what are these things? Definition: a description of a system using mathematical concepts and language. Here, a system basically means a group in which you have these actors, these entities that influence each other. So for instance, I'm going to use this example later on, but let's consider an island. And in the island, there's moose and wolf. The wolf is going to eat the moose, which means that the wolf population is going to have a negative impact upon the moose population. But on the other hand, if the wolf population declines, the moose population is going to increase and vice versa. So this kind of group where these entities, these actors constantly influence each other, this is a system. And the other key term in here is mathematical concepts and language. So mathematical concepts and language are basically, as you have seen in the previous 2 examples, in here, this is a mathematical depiction of a system of GPA versus time spent studying per day. You used logarithms in order to represent the 20 data points. So this is how mathematical concepts are used to depict this real life situation. Well, on the other hand, in the case of this discrete models for tissue growth in a test tube, this is a model constructed by using physics equations, things like biology, about the interaction between these cells, these interactions on a molecular level. So this is also how you represent a real-life scenario using these differential equations, using physics, using mathematical concepts at the end. So how do you construct these models? And this is where the 7 steps of modeling come in. As I've shown you through the 2 previous examples, a model is basically mapping a real-world situation, the one on the left side of this presentation, to a math world, to basically mathematical concepts. So on the leftmost corner, you have something called describe the real world problem. This is where you analyze a real world problem and try to think about how that can be represented into mathematical concepts. This will be much more clear when I show you an actual example, when I tell you about the system dynamics models, but please bear in mind that the most important part of a model construction is to describe the real world problem and try to analyze it, try to break it down. And then we try to map this real world situation to a math world. So this is where you specify the mathematical problem. This is where you try to set assumptions, you try to set variables in order to convert this problem into the math world. And then the third step would be what happens inside this math world. This is formulating the model. This is representing all the variables, these kinds of concepts that you have described into a math equation or these lines of codes, these computer science codes. And then after you formulate the model, you can solve the mathematics. And then after you solve the mathematics, this is going back into the map between the real world and the math world. You interpret the solutions to find the implications or the potential applications of the solution that you have found. So if you get, so in the previous example of GPA versus student time in studying, if you've got a logarithmic equation, then you can infer that at first, the more you study, your GPA is going to increase at a very fast rate, but then at the end, it's going to increase at a much slower rate. So these are implications that you can find from a mathematical model. After you interpret the solution, you can evaluate the model by using real-life data. You can compare what you have got from your equations to what is actually happening in the real world and estimate how accurate your model is. And if your model is not sufficiently accurate in your opinion, then you can go back to specifying the mathematical problem. I talked about making assumptions, right? So some assumptions can be safe to make, while other ones can be quite bold. So if you evaluated the model and you think that your model isn't really accurate enough, you can go back to change your assumptions, make new variables so that it is more reflective of reality. After you specify the problem, this is again a loop of formulating the model, solving, interpreting, evaluating, until you think that your model is accurate enough. After this happens, you can just write a mathematical report, and this is basically the 7 steps of constructing a model. But in the previous 2 examples, this one and this one look quite different, right? Because this one was based upon data points. This one was based upon empirical data. But on the other hand, in the context of this model, we didn't have enough information. These equations, these 4 systems of equation clearly don't look like the line of best fit like this one here. So this is where we have 2 different ways of constructing these models. The previous thing that I talked about, the 7 steps apply to both, but this kind of differentiation is about how much information that's given before you go into that 7 steps. So the first one here is called a white box method. In computer science, if you're interested in computer science, you will know that a white box is a situation where you know the internal mechanisms of something. So when you put in data and you get the outcomes, but you know what is actually happening inside there, we call that a white box or transparent box. And on the other hand, if you know that data is going in and some kind of result is coming out, but you don't know what happened in between, we call that a black box because we do not know properly the internal mechanisms. So here, a white box method would be a situation where you have ample a priori information. So that is, when you already have lots of empirical data, where you already have information about how this kinds of real-life situations actually work. And when you have all necessary information, so for instance, the example that I gave you about GPA versus time spent studying per day, we already had 20 data sets, which is sufficient to construct that equation there. So this is where you use the white box method, where you have already sufficient information. But on the other hand, a black box method would be this discrete models for tissue growth in a test tube. This would be a perfect example of a black box method because we don't have we don't have empirical data about growing tissues in a test tube. We just haven't done that yet. So in a situation where you do not have a priori information, we would use other kinds of information that we have. So for instance, the physics equations about interactions between cells on a molecular level. We could develop those kinds of equations into the model that we have there. So this is when you have to decide variables, set assumptions, and so on. But the important thing is that most of the cases, if not all, construction of models is a combination of white box and black box situations. So for instance, consider a situation where you're trying to model the spread of medicine A in the human body, or arbitrary medicine. So researchers might know about how this medicine works, but we might not have exact information about who is taking this medicine, or how much of this substance, how much of this compound is already in the human body. So because those informations are not available to us, we have to make some assumptions, or we have to set some constants so that it is reflective of our reality as much as possible. And that is where modeling becomes a combination of white box and black box scenarios. It is best if these models are dependent entirely upon white box scenarios, these white box information, because those would be obviously more reflective of reality. But just as the example that I gave you, we have to make some assumptions and set some constants at the end. And hence, because we set assumptions, all models are wrong. This is a famous aphorism in data science. But an important clarification is that some models are close enough to reality that they're good enough to use. And because no model is perfect, because no model is 100% right, we have to use multiple heads. And there are many ways to prove that multiple heads are better than one. When you're talking about non-numerical models, ones that simply predict about which one is going to be better than which one, use something called the Condorcet-Jury theorem in order to prove this. If you're talking on numerical models, where you are having quantitative data, when you're talking about a situation being this much better than another situation, then you use something called a diversity prediction theorem. So the Condorcet-Jury theorem is that we have these three preconditions here. First, we have n people where the total number of n people is odd. And two, each person makes a binary choice. So that is, each person votes either true or false. And finally, each person has an accuracy of 1/2. Then, with these three preconditions, the Condorcet-Jury theorem effectively states that the more people we have, the more the accuracy of the majority vote approaches 100%. In order to prove this, you can just calculate the probability that n-1/2 plus 1 people will be right, n-1/2 plus 2 people will be right, all up to n people being right. And using the binomial theorem, just expanding that would give us an expression that yields a numerical value that approaches 100% as n approaches infinity. And the reason why this can be applied in mathematical modeling is change people to models. If we have n models where n is odd, and if we say that each model has an accuracy of over 1/2, then it means that the more models we have, the more the accuracy of the majority would approach 100%. So from this, we can know that the more models we have is going to be probably far more accurate. In the context of numerical predictions that we are making, we have something called a diversity prediction theorem. In the equation there, C represents average of crowd prediction, while X represents the true value of something. You can prove the equation by just expanding the brackets, and you would get that equation is right. But what we can know from that equation is that the crowd square error equals mean square error minus diversity of the crowd. So this is just simply saying that the crowd's error would decrease if the diversity of the crowd increased. And this is because the positive errors would cancel out the negative errors. If we have a true value, and we have, like, say, 11 models, and let's say that 5 models among them are quite accurate, they're around the actual value. But if we have 3 models that predict a numerical value that is significantly higher than the actual value, we will also have 3 models that would predict significantly less than the actual value. So at the end of the day, the more models you have, the positive errors would eventually cancel out the negative errors, which means that the net prediction would be far more accurate. So this is why having a system with many models, a many model prediction is far better than a single model prediction. But enough of talking about like these meta science things. Applications, how do we actually make these? I'm going to talk about system dynamics models within the application. So what is a system dynamics model? SDMs are models in which the relationships between entities depend on the other entity. So I'll give you an example. So please take some time to read the excerpt here. So in here, we have a wolf population and we have the moose population, which constantly affects each other. If the moose population increases, it means that they would prey more on moose, and thus the moose population would decrease. But on the other hand, if the moose population decreases, then the wolf population would also decrease because there's a smaller amount of food. And when the wolf population decreases, the moose population would in turn again increase because now you have less predators. So this is an example of a situation where you need a system dynamics model, because the wolf population and the moose population constantly affect each other at different rates, at a rate that constantly differs. So we call this 7 steps. We're going to use these 7 steps in order to construct a really simple model. First, describing the real world problem. Let's use this diagram here. The circle that says M represents the moose population, while the circle that says W represents the wolf population. Here, the arrows are supposed to represent whether it has a positive impact or a negative impact. Here, the moose population and the wolf population would both decrease even with the absence of each other, because there is something called a mortality rate, right? And also, because both populations reproduce, we would have a self-perpetuating cycle where you see the circular arrow saying plus. While on the other hand, the moose population would have a positive impact on the wolf population because wolf prey on moose, and therefore the wolf population increases, while on the other hand, the wolf population would have a negative influence on the moose population. So we first describe the real-world problem like this. Then we can specify the mathematical problem using this diagram here. First thing, we'll establish a continuous model because we see that the rate at which the two actors influence each other continuously varies. So we're going to establish a continuous model. So that is, we're going to use things like differential equations. And second, we're going to consider the situation to be equivalent to collisions between moose molecules and wolf molecules. This is the assumption that we're going to make. Because we cannot perfectly know where a single moose is going to be at some kind of time, we have to assume that this is equivalent to random moose molecules and random wolf molecules roaming around the island and colliding to each other. And 3, weights are going to apply uniformly. So that is like, if we have a variable about the rate at which moose population declines when moose and wolf meet, that rate is going to apply uniformly to every single collision between moose and wolf. So these are the assumptions that we're going to make. Then we'll set the variables. I think that there are mainly 6 variables in here. First of all, the moose population, wolf population, quite obviously. Second, G, which represents the moose population increase rate if the wolf did not exist. So this is the rate at which the moose reproduces. D, which is going to be the wolf mortality rate when the moose did not increase. So this is where the wolf just naturally die. And A is going to be the rate at which the moose population declines when wolf and moose meet. B, on the other hand, is going to be the wolf population growth rate when moose and wolf meet. All of these variables, all of these things are going to be constants, and you can get these by empirical data. Then we get these two systems of equations. First, the rate at which the moose population differs is going to be its growth rate minus the rate of predation. So the rate at which the moose is eaten by the wolf. On the other hand, the rate at which the wolf population differs is going to be rate of predation minus the decline rate. So that is, the rate at which the wolf population increases thanks to eating the moose minus the rate at which it declines because of just natural death. So first of all, the growth rate can be modeled by G times M, because we know that population increase, if the wolf did not exist, is going to happen at an exponential rate. We just simply multiply G, the increase rate, to M, the entire population, and we would get the rate of increase. And in terms of the rate of predation, because we assume there is a random collision between moose and wolf, we will multiply A times M times W. And then by just simply subtracting these two, we would get the rate at which the moose population changes. In the same method, we can apply the exactly same thing to the wolf population as well. Because we set B as the growth rate when moose and wolf meet, just as we did for the rate at which the moose population differs, we will multiply B times M times W and subtract dW from that. And dW is the wolf mortality, is the rate at which the wolf population declines if the moose population did not exist. And using these systems of equations, we already modeled about how this moose population and wolf population, how this interaction is going to change within this island. And we can solve the mathematics. Well, we could also get a we could also get a solution for this differential equation here. Let's just talk about this equation we have here. We would get an interior equilibrium when F equals G over A and H equals D over B. This is because if we just plug in those values, we would get that the rate of change of M would equal 0 and the rate of change of W would equal 0 if F equals this and H equals that. And we can also interpret the values that we got from this. Because F is solely dependent upon G and A, we can know that this doesn't really depend upon wolf birth rate and moose death rate. And we can explain this by saying that the wolf birth rate and the moose death rate kind of cancel each other, so thus the two do not have a significant impact upon how the populations would vary. Another interpretation that we might do is that the extinction happens at F equals H equals 0. So that is the moment when both populations do not change. And another interpretation that we can also do is by graphing the system of equation that we got. We can just plug in some arbitrary values and we'll easily see that there's a cycle. So within the cycle, if the prey population increases, the predator would also increase, and hence the prey would decrease, which is exactly what we formulated when the first step of constructing this model. And after we do these kinds of interpretations, we can evaluate the model. In fact, this example of KGSEA Island is something that actually happened in a place called Al Royale. So this is the graph of how the moose population and the wolf population actually changed in that island. And comparing this with this, we see that the graph is significantly different. And there are many explanations. For instance, here you can see that a severe winter decimated the moose population. Also, you can see that the moose reaches extreme density or whatnot. And by evaluating the model, you can see which ones of your assumptions were quite wrong, which ones are quite far from reality. And you can go back to the first step of formulating the equations, setting the mathematics to adjust your original model so it's more reflective of reality. And also within the evaluations, we can talk about applications. The previous two systems is actually called a Lotka-Volterra equation. These are wide applications in disease, predator-prey situations, and all kinds of system dynamics, and all kinds of situations where system dynamics models are needed. Especially in a disease modeling, many of you guys would have heard about the SIR model. This is where there's a susceptible population, the population that hasn't contracted the disease yet. You have an infected population, and you have the recovered population. All of these three entities, affect each other at differing rates. So for instance, if the infected population increases, it means that disease is going to spread far more rapidly because you now have more contacts between infected people and susceptible people. However, on the other hand, if the infected population decreases, it would also mean that the susceptible population would go over to the infected population at a much slower rate. So these Lotka-Volterra equations, the same principle can be applied to these kinds of disease modeling or other real-life contexts as well. So that's it for me.